Okay, my name is Lemnitzer. I'm at UC Irvine. And as Frank said, this part of the topic that we're studying was just one of those that just got very recently funded, so we're just about to start. So I will show you a little bit of what part one was about, and then the vision and the ideas that we had in order to move forward. So it's basically a statistical assessment of the uncertainties that are inherent in soil resistance functions, and by that I mean the most commonly used tool, especially here on the West Coast, which are PY correlations. And we had a project team that carried over from our part one, and we assembled that as a group of members from academia, from industry, from government, and within those, some serve more in a writing role, some serve as an advisory role. And so the idea was to get a broad perspective and establish a series of reports that would kind of serve as an update. So within the part one, and that's what I presented in the previous annual meeting, that part one was a state of the practice, state of the art report, where we look at existing modeling approaches, heavy focus on soil resisting functions, what is out there, what has been done since API recommended the early studies in the 60s and the 70s, and basically collect what researchers have contributed to the literature and make others aware and bring it in a form usable by practitioners. Most of us, maybe here in the room, who work in that field, they know, oh, this guy has done this load test and this guy has done this load test and derived PY relationships. But a lot of the people using it as the end user in programs like LPIL, etc., they do not know. And that is one step in that direction. Part two is what we're doing right now is a statistical look at the existing relationships. And then part three is more a vision out to do validation studies and then develop maybe revised guidance, documentation, and recommendation. I showed this earlier in the year in the annual meeting as part of that part one report. We did an extensive survey among practitioners and users of various softwares, analysis approaches, etc. And one of the questions was, which type of analysis method do you use for your lateral deep foundation design the most? An overwhelming majority, so please note it doesn't add up to 100 because people could pick several options, right? They're not bound to one. 92% of the people said, oh, we're using PY type of analysis. And then a few others trickle in with finite element difference or rigid or limit states. And then among those that say, those 92%, 71% say we use PY 100% of the time, and it's our only tool that we rely on for lateral pile design. 19% said about 75% of the time we're using it, and then about 9.5% they say, well, we don't use it so much, we use more advanced. So the problem to be addressed is literally the pile behavior from various aspects. I'm going to start with the soil first, and we're going to go through some structural and some boundary stuff. So lateral pile resistance is strongly dependent on soil properties. If we imagine we use one and the same pile, place it in different kind of soil strata, then we know within the upper, 5 to, let's say, 8 to 10 pile diameters, your soil plays the big contribution. Where do we get most practitioners and us their soil data from? Well, SBT and CBT correlations. The survey showed actually that SBT was over 80% of the time. Correlations that are being used most frequently are the ones that are 20 to 30 years old, the ones that API recommended, and little information is known regarding the uncertainty of those. Everyone knows, oh, they're uncertain, they're over-predicting here, underestimating there. But then when you say, oh, by how much, there's not a lot of precise data available. So when you go into the API recommendations, the key input that you would need for your soil spring analysis is the stiffness K. And that's what programs like Group, LPIL, etc. are asking you for. It's that stiffness parameter K. And that is plotted as a function of relative density and friction angle of the soil. Well, these are the relationships that are listed in the code and most people use. And there's a curve that exists for sand. This is the example here for sand, above and below the water table. And so before we started this, we just did a little trial analysis. And we looked at 2 test sites, one of them being this one. One of our team members, Kyle Rollins, he tested, you might know the testing program between him and Scott Ashford on non-liquefiable and liquefiable deep foundations on the Treasure Island site. And that has a sandy type of fill. And when you look at the soil data, they had a cone resistance available, also SPT data available, and you would get the relative density from those in situ correlation with which you enter your API curve. And they used that, got their data, the API recommended input parameter, and then compared it with the measured data and checked what would have been the input parameters that I needed to match my load displacement relationship versus what are the ones that I received by just entering the code. And you see here, well, what API recommended, or what API equivalent would have been a friction angle of 34 degrees and the corresponding soil strength. What was back calculated to actually match, and here by focusing on mainly the upper 20 feet of the soil, was 39 degrees. You might say, well, only like 5 degrees back and forth, that's an uncertainty we have to take, and it happens all the time, but it has an effect on the ultimate response. So they decided to look on another example. This is a test series at the point of mountain testing, and there were several hollow steel piles that were driven there, and they were subjected to lateral loading, eventually also under slope loading. And the relative density of the sand is about 50%. And when you go in your curve right here for 50%, your corresponding angle of internal friction, or soil strength, corresponds to about 33 to 34 degrees from API. If you use that to put this into your ALPA analysis, it determines decay, advanced analysis, you would get your results. And then he said, well, let's see, and what would have been the friction angle and the parameters that would have matched our test results. And so Kyle made a little student experiment out of this. And here on the left are all the students that were part of that assignment. And they all used the same pipe pile, the type of reinforcement that was in the field. And instead of 33 degrees, that is down here, they all ended up getting 39 to 38 degrees. And when you go back to that plot right here, whether you enter a curve here or whether you enter a curve where the stiffness out here and you go across, it makes quite the difference, by a factor of 2. So when we look at this relationship in terms of relative density and friction angle, here's the correlation that API proposes and that most people are using out in the practice. Here is the correlation that would correspond to the Treasure Island site and also to that point of mountain test site that you see right here. It's a much higher value than what was predicted. When you go back to some previous testing by Brown, technically in order to match his test data, the soil would have needed a friction angle of about 50 degrees to push your ALPI and API predictions up to what was in the field. So when we go back to that very first graph that I showed you out of the code, and we plot the data points in here, you can see between relative density and friction angle and K that the K values are substantially higher than what the curve would have given you. And that's just that very simple little exercise was a stepping point or a starting point for looking at the statistical variation in those curves with respect to the soil parameters. And so what our objective is for the study is to look at those 3 components. to look at the soil component, to look at the overall pile soil behavior with the focus on the structural, and then perform a blind prediction. So we currently, as I showed you, we started looking into just assuming we look at the similar piles with similar stiffness and bending behavior. What is the uncertainty involved in those PY resistance function with respect to soil? So we collected 30 field studies, 15 in sand, 15 in clay. We're trying to get this up to 20 to have a bigger variability. Digitized the data, pulled it out, primarily load displacement, PY if they derived it, and moment versus depth. Digitized soil data as available from SBT, CBT tests, and then created case histories in LPIL to just run that very simple analysis to see where we are. This is part one, focusing on the soil. We also are interested how the existing functions vary for a given soil structure combination. So let's say you do have a steel pile and you have a bunch of clay PY curves that various researchers recommended, right? So while study A shows you that orange curve, study B for their test derives this general PY curve, the next one this one. That difference in here might not look that big to you. Once you translate it in a whole series of springs along the pile, your load displacement looks substantially different, and also your pile profiles. So what is that range that is available, and what basically uncertainty and variation is involved with respect to where we end up in ultimate capacity and in stiffness versus displacement? Everyone knows those curves are out there, but we have found very little information of someone actually compiling it and showing it and looking at it, which relationship gets us the closest or comes up with an approach that includes more parameters to get us closer. So we're going to look at this for various cases, and then in the end we would like to do a kind of a blind prediction. And I have spoken with a few people, and we don't want to know the data either, because I do have a large database where I could kind of cheat and look it up. So I asked two people that, one from Dan Brown and also another person who works with Caltrans, to see if we can get a test that is not published, where we would only get the data that every practitioner out in the field would also get, which is like a SBT or a CBT profile, perhaps a head load displacement data, and then try and do our own analysis and see how close we would get in predicting that response, or which relationship gets us the closest there. And if we do that for several studies, and then our vision is to combine all of this in an uncertainty report and move forward from there by simply presenting what is available and how close can we get with what is available and how can this be improved. So this is step 2 within the study. And then from there on, I guess there would be a path towards validation, towards modification, and towards supplementary numerical studies before eventually we can, start providing a recommendation or an update to some of the existingly used codes. And the nice thing about this too, we have the collaboration with both. We eventually, right now we have one person from NSoft and also one person with OpenSeas on our project team. So whatever comes out, we would like to disseminate and implement that in those software platforms as well. So if you have any ideas on how to expand it, or if you have a experiment that can be used for that blind prediction, let me know. It needs to be something that none of us in the team knows yet.
So any questions, suggestions for Bill?
Actually, I'm sorry I cannot help you, but I just have a question of somebody who is not very familiar with the analysis. So in your analysis, you are using a 2D model, so this is just basically something like sort of a column element with springs only in one dimension, and are these spring properties that you are supplying or the API recommends, are they accounting for the three-dimensional behavior of the soil, or is it, so how exactly does one reconcile this with reality when you want to go and
Yeah.
look at the test?
You're right, like with Alpa and what everyone in practice uses, it's not 3D. Group, which is Alpile's extension for sets of pile groups, they are going into 3D, but Alpile is not. It's when I mentioned you have your beam or your column element.
Yeah,
and
but I
then
am
you
assuming that
represent-
somehow the soil properties do account for 3D behavior.
Yeah, inherently because they're empirically derived, but the analysis itself is not 3D, right? Same, yeah.
Pedro does 3D, but it involves context
Yes.
and stuff.
And Pedro is on the
Right.
team too.
And Pedro's up next.
One of the things that you might want to focus on is just sites that have CPT data and shear wave velocity.
Yes,
In other words, leave SPT out in the dust. If you're going to actually go forward and have good statistical relationships, you want shear wave velocity and you want CPT.
that's one of the main recommendations in that part 1 report.
So even going
100%.
back to some sites that are well-documented tests and
Yeah.
doing CPT after the fact would be better than sticking with SPT.
Yeah, 100% agree.
Pedro?
Yeah, and a lot of what we know about the feedback curves is based on lateral load test and piles.
Mhm.
And when you do a lateral load test and a pile, you usually engage a zone in the soil that is very close to the surface.
Mhm.
So you don't know how is the response down there at a certain depth. So something to investigate is how are the feedback curves at depth. Usually we extrapolate what we see in the surface, boom, and then we go, yeah, use a certain depth. But then the stiffness correlation that you have and the P ultimate parameters that you use may not be valid. So maybe that's something to look when you investigate the validity of this.
You mean like a depth dependency?
Yeah.
Right, that correlation and the validation thereof? Yeah.
Tom?
Good idea.
Well, along those lines, typically a bottom of pile cap is usually going to be 5 feet down at least or something, and so there's likely to be a fair difference between under those confining stresses and up near the top. The other thing that seems to be lacking in this project is any consideration of the pile itself, in that an open-end pile will more or less core through the soil, especially up near the surface, so you're not going to develop the same radial stresses that you're going to develop if it's a closed-end pile. And so for your initial stiffnesses, you're likely to see a big difference. Well, I would think a significant difference in
Yeah,
in
and
that case.
I agree with you. That's the one reason why I'm still looking for good data like crazy, because I don't want to compare a steel pile with a concrete pile, and just in terms of the whole bending behavior, because it changes it.
Yeah.
And I approach it more from a structural perspective, but I would say that the structural bending behavior and just the reason, like the way how the relationships are derived, the structural properties influence it more than the soil.
Yeah, no,
But
I think
I
that's probably
don't-
true in concrete.
I
It's
do not
really
get a
hard
lot of
to.
favor among geotechs with a statement like that, but it has shown in all the research that derived it, and it's because the way how we derive it. But yeah,
Anything else?
if you have 50 more tests in your sleeve, I'd be happy to take this data.
Sure.
My only suggestion would be like put it on some sort of database, some relational database,
Yeah, so,
accessing the data.
so we do have one, it's findapile.com. There are 50 load tests right now that we digitize, and I have 30 more that I actually need to put on there. Not everyone, and that goes back to what John said, has really good data, because, and it's a mess to digitize really old reports with hand-drawn SPT data. So, yeah.
Frank, and is there any value to look into piles that have different boundary conditions at the top?
Yeah,
That
Yeah.
would be pretty awesome to have.
I know, the free head versus fixed head.
Right.
Yeah, Professor E.T., with him we did a study, and him and his student have a paper, and in there we clearly show how that makes a huge difference in the PY curves that have boundary conditions.
One last question?
Yeah, we did dynamic tests on piles here on campus for our seismic program, and that's published. It's ERC published. I mean, it's peer publication. And
It's under
real-
peer
real
publication?
It's real dynamic test data. It's published in all over the place, and it's been modeled in even open seas. There is a constantly model for the piles, so you guys have it. Just
I have to check, it might actually already be on the database.